So she's going to start recording, okay? So good afternoon to everyone, and welcome to the fourth day of the workshop on finite fields and applications. So it's a pleasure to introduce the next speaker. That's Massimo Giulietti from the Università degli Studi di Perugia. He's an expert on algebraic curves, and he's going to talk about algebraic curves with many automorphisms today.
Thank you, Luciane. First of all, I'd like to thank the organizers for inviting me. It's really a great honor for me to have been invited to give a talk at this workshop dedicated to the memory of Fernando. When I first met Fernando, I was just a PhD student, and he was, of course, a great inspiration to me. Later, during the years, he visited Perugia a number of times. I went to Campinas once, and of course, we had many mathematical discussions, but we also shared football matches, jazz concerts, trips, and I was very lucky because I had the chance to appreciate how special he was, both as a mathematician and as a person. And I think that as everybody in the audience, I miss him a lot. Well, today I'm going to discuss some results. I'm going to summarize the results obtained in the last decade or so about curves with many automorphisms. As usual, by curve, okay, I will mean a projective, non-singular, geometrically reducible algebraic curve embedded in some projective space. The projective space is over a field, which we assume to be algebraically closed, but we don't make any assumption on the characteristic of the field. And in fact, our main target is the positive characteristic case. As usual, G will denote the genus of the curve. And what is an automorphism? An automorphism of a curve X is a birational map of X to itself. That is an invertible map, roughly speaking, defined in homogeneous coordinates by homogeneous polynomials of the same degree. If the curve is a plane non-singular curve, actually the automorphism group is just the group of linear transformations preserving the curve, provided that the degree is at least 4. And this is a deep result going back to Beniamino Segre, 1933. Let me recall that any curve has a plane model, a possibly singular plane model. That is, it is birationally equivalent to a plane curve with a finite equation fxy equals to 0. And with a slight abuse of terminology, we will say that fxy equals to 0 is an equation for x. Now, research in this area received a strong impulse from the publication of this book by Fernando, together with Gabor Korczmaros and James Hirschel, Algebraic Curves over a Finite Field, published back in 2008. And probably it can be said that there have been more achievements in this area in the last 13 years with respect to the previous 30 years or so, at least in the positive characteristic case. Now, if a curve has many automorphisms, it is not just a nice curve because it has a lot of symmetries. But interestingly, many other curves can be defined from it. And often these curves inherit relevant, important properties of the original curve. These are the so-called quotient curves. I'm not going to recall the precise definition of the quotient curve. I'm just going to say that when you have a finite group of automorphisms, it acts faithfully on the set of points of a curve X. And there exists another curve, let's say X over G, and the projection such that 2 points have the same image if and only if they lie in the same orbit under the action of the group. As a matter of notation, by θ1 up to θk, we will denote the short orbits under the action of the group G. This is a very famous formula, the Riemann-Hurwitz genus formula, which relates the genus of X with the genus of the quotient curve. It's important to note that in the zero characteristic case, the formula only depends on the action of the group. In fact, the contribution of a point to the different here is just the size of the stabilizer minus 1, stabilizer of that point minus 1. In the positive characteristic case, instead, to the contribution, for calculating the contribution, we need to take into account also higher ramification groups, and this makes a very big difference. Okay, now curves with genus 0 or 1 have an infinite automorphism group. These curves are actually the only exceptions, since any curve with genus at least 2 has a finite number of automorphisms. In the complex case, this is a very classical result going back to the German geometry school of the 19th century. The first characteristic free proof probably goes back to Schmidt, 1938. Then we had a number of different proofs, for instance, by Iwasawa and Tamagawa, Roquette, Rosentlich, and more recently by Arnaldo Garcia. The classical Hurwitz bound in the complex case is 84 times G minus 1. Okay, a Riemann surface can have at most 84 times G minus 1 automorphisms. And the classical proofs works without much alteration over any field with characteristic 0. An example, the best known example of a curve attaining the Hurwitz bound is the Klein quartic, a curve with the equation x cubed plus y cubed equal to 0. It is a non-singular quartic, so the genus is 3, and the automorphism group is PSL to 7. So the Hurwitz bound is attained. Now let me spend just 1 minute on curves attaining the Hurwitz bound in 0 characteristic. Back in 1961, Macbeth showed that there are infinite genera for which there exists a curve attaining the Hurwitz bound, and that the second smallest case is G equal to 7. And in that case, the automorphism group is PSL to 8. A curve with this property, or better, a Riemann surface with this property, was constructed by Robert Fricke back in 1899. But the first equations describing this object as an algebraic curve were found by Macbeth in 1965. Hendricks, 2013, found equations over the rationals, but a plane model with integer coefficients only appeared a few years ago by Hidalgo, who referred to an unpublished result by Brock. Okay, we will come back to this curve before the end of the talk. And let me stress that no other example whose explicit equation is known for curves attaining the Hurwitz bound. Now, if P does not divide the size of the automorphism group, then the Hurwitz bound still holds. But if P divides the size of the automorphism group, then the curve may have a much larger number of automorphisms with respect to the Hurwitz bound. For instance, let's consider the Hermitian curve. Hermitian curve, non-singular plane curve with the equation x to the n plus 1 equals y to the n plus y, where n is the power of the characteristic. The genus is, of course, 1/2 n times n minus 1, and the automorphism group is PGU3n, roughly n to the 8 elements. Okay, so we have roughly 16 times g to the 4 automorphisms. Okay, huge difference with respect to the Hurwitz bound. What is the reason? Well, the main reason is the appearance of P groups, that is, groups of size a power of P, fixing a point. Let me explain this phenomena very, very briefly in the easiest case, that is the case of a non-singular plane curve. If you have a an automorphism fixing a point, then it also must fix the tangent line. And if you have a linear transformation of a line fixing a point, then it is either it generates either a cyclic group fixing another point, or is a translation of the line, or fixes the line pointwise. That is a translation of the plane. But in zero characteristic, translations have infinite order, and so they cannot appear in the automorphism group of a curve. In characteristic P, translations have order P, so it may well appear in the group. Let's have a closer look at the stabilizer of a point in the automorphism group of the Hermitian curve. Let's consider the infinite point of the Hermitian curve. Here you have a description of the stabilizer. Stabilizer whose size is n cubed times n squared minus 1. And if you think at the zero characteristic case, then the only transformations that survive are those with b equal to 0 and c equal to 0. That is only n squared minus 1 transformations. Okay, in general, we know a lot about the structure of the stabilizer of a point. More precisely, if we denote by SQ the CeLO P subgroup of the stabilizer of Q in G, if P divides the size of the stabilizer, trivial group otherwise, then we know that the stabilizer is the semi-direct product of this CeLO P subgroup times a cyclic group. Okay, very strong result. What about classification result? Stichnot back in '73 showed that the Hermitian curve is the only algebraic curve with more than 16 times g to the 4 automorphisms. Hen brought deeper group theory into the subject and was able to classify all curves with more than 8g cubed automorphisms. More precisely, you have this hyperelliptic curve in characteristic 2, the hyperelliptic curve with the equation y squared plus y equals x to a 2k plus 1. This hyperelliptic curve in the odd characteristic case, y squared equals x to the n minus x, where n is a power of p, the Hermitian curve, or the Suzuki curve. I guess many of you, maybe all of you, know the Suzuki curve. The Suzuki curve is defined over fields with characteristic 2 by this plane equation, x to the n0 times x to the n plus x equals y to the n plus y, where n0 is a power of 2 and n is twice n0 squared. A couple of remarks. In the book by Fernando, Gabor, and James, you can find the first proof written in English. The original paper by hand was written in German. And also some little gaps pointed out by Nakajima are filled in the book. Also, each of the above 4 curves is characterized by genus and size of the automorphism group. A beautiful result in this direction is this result by Fernando with Fuhrman, 1998. They characterized the Suzuki curve as the only curve with that genus at that number of Fn squared rational points. And as a personal note, this was the first paper by Fernando that I read, and it was just fascinating to me. Okay, if the group has a special structure, then we have different bounds. For instance, Stichnot showed that if you have a cyclic group of order not divisible by the characteristic fixing a point, then its size is at most 4g plus 2. Nakajima in '87 proved this bound for abelian groups, 4g plus 4, actually 4g plus 2 in the even characteristic case. And Fernando in '95 wrote a paper published by an Italian journal, Rendiconti di Trieste, in which he found other bounds under other conditions. For instance, for groups having a non-trivial set. Now, in positive characteristic we have another important invariant for a curve other than the genus. This is the P-rank. That the P-rank has a great influence on the automorphism group was already noticed by Subrau and Sullivan back in the 70s. Now, the P-rank can be recovered from the Jacobian variety of the curve, or equivalently from the zero Picard, from the Picard group P0x, the zero divisor class group. This group is an infinite group, but for any prime L, the subgroup consisting of the elements of order L together with the identity is a finite group. If L, the prime L, is different from the characteristic, then this group has precisely L to the 2G elements. If L is equal to the characteristic instead, then the size is still a power of P, but the exponent is at most G. Okay, and the actual exponent, in other words, if this group has P to the gamma elements, then we call gamma the P-rank of the curve. And it coincides with the Hasse-Witt invariant of the curve. I already said that the gamma is at most equal to the genus. If equality holds, then we say that the curve is an ordinary curve. We have a formula which is actually the analogous to the Riemann-Hurwitz formula for the genus. This is the Döring-Schafarevich formula. It applies only to P groups of automorphisms. But it is a very powerful tool because, as you can see here, you have the P-rank of X, the P-rank of the quotient curve, and here only the sizes of the short orbits. I mean, higher ramification is not involved in this formula. Couple of remarks. In all the examples from Hahn classification, the P-rank is actually equal to 0. And interestingly, maximal curves over finite fields all have P-rank equal to 0. On the other hand, ordinary curves occupy an open dense subset in the moduli space of curves of a given genus. So we might say that the most interesting cases are the opposite sides of the spectrum, gamma equal to 0 and gamma equal to the genus. Okay, in the book, the book by Fernando, James and Gabor, an innovative approach is presented for investigating curves with P-rank 0. And it is based on this straightforward consequence of the Döring-Schafarevich formula. For P-rank 0, the formula reads this way. Okay, -1 equals minus the size of the group plus this sum for E going from 1 to K, size of the group minus size of the short order. On the left-hand side, you have an integer which is, of course, equal to -1 mod P. And so it must be the right-hand side. This means that you have only one short orbit, and this one short orbit must consist of a single point. In other words, every P group must fix a point and must act semi-regularly on the other points of the curve. And in particular, this means that any two zero P subgroups of the automorphism group have trivial intersection. And this is a very strong property. It's a purely group theoretical condition which allows to use deep theorem from finite group theory. For instance, the Burnside-Gauss theorem for the solvable case. Okay, let me end this introductory part by recalling a seminal paper by Nakajima, going back to '87. In that paper, Nakajima proved a number of things. For instance, that if you have an ordinary curve, that is P-rank equals the genus, then the automorphism group cannot be larger than 84 times G squared minus G. And this bound is not sharp. We'll come back to that later. He also provided some bounds for the size of P groups of automorphisms. I summarized these conditions in the bottom line. If you have a P group with more than 2P over P minus 1 times genus, elements, then the P rank must be equal to 0, and the group must fix a point. Okay, so this is a bound for the case of a positive P rank. In case of P rank 0, then the bound is a fraction of G squared. Okay, let me show you. For P over P squared, so roughly 1 over P times G squared. Okay, next I'm going to deal with some natural problems that have received much attention in the last years, and for which some substantial progress has been made. First, bounding the size of the automorphism group under some extra conditions, either on the invariance of the curve or on the structure of the group. Second, classifying curves attaining the above bound or almost attaining the above bound. And third, classifying groups for significant classes of curves. Let me briefly recap the starting point, that is what we know from the results that I have recalled so far. I have distinguished in this slide 3 cases: gamma 0, gamma G, and the intermediate case. Okay, let's start with gamma equal to 0. For a generic group of automorphisms, the upper bound is 16 G to the 4, roughly. Okay, as a result, provides this green segment. Okay, by this green segment, I mean that we know everything in this interval from AG cubed up to 16 G to the 4. We know what are the curves here. If we restrict our attention to P groups, then the Nakajima upper bound is a fraction of G squared. And we would like to have some characterization in this part here. We don't have it, okay? This is our first question mark. Finding, classifying curves whose size of a 0P subgroup is close to the Nakajima bound. Okay, what about the intermediate case? We don't have any satisfactory bound for a generic group. We have a trivial bound, which is AG cubed, because we know that every curve exceeding AG cubed has P rank 0. Okay, but we suspect that we can do much better than that. But it's a difficult issue. What about P groups in this case? Nakajima bound is roughly G, is linear in the genus. We would like to classify curves attaining the bound or close to the bound. Finally, for ordinary curves, we have Nakajima bound 84 times G squared minus G. I already anticipated that this bound is not sharp. Well, let's try to improve the bound. And let's try to construct ordinary curves with many automorphisms. As to the P groups, the situation is the same as the intermediate case. So let me begin with this problem here, okay? Large P groups, P rank 0. A number of years ago, in a series of papers, Ler, Matignon, and Rocher proved the following results. Okay, recall that the upper bound is roughly G squared over P, okay, the Nakajima bound. Okay, Ler and Matignon first showed that if for gamma equal to 0, you have a P group whose size exceeds G squared over P squared times 4, then the commutator subgroup of S is ZP, the cyclic group over the P, and the curve is of this type, is an artificial extension of the projective line. More precisely, the equation is of this type, y to the P minus y equals x times f of x plus c times x, where f is an additive polynomial. They also were able to say something for groups larger than G squared over P to the 4, roughly. Here, the possibilities for the commutator subgroup are 3, that is ZP or ZP squared or ZP cubed, okay? always an elementary abelian group, and some characterization was given, not as clean, let's say, as the previous one. Together with Gabor, we dealt with this bound. Okay, we assumed that we had a P group whose size was bigger than G roughly, okay, 2P over P minus 1, under an additional hypothesis. The additional hypothesis that the automorphism group, the full automorphism group, doesn't fix a point. This extra hypothesis makes sense because if the automorphism group fixes a point, then it is the stabilizer of a point. And so we know the structure, okay? You already know the structure. And we were able to prove that if we have more than this number of elements in a P group, then the curve must be one of these four curves. BCD in N's classification result means the hyperelliptic curve in odd characteristic, Hermitian curve, Suzuki curve, and then we have also the possibility that the curve is a recurve. Again, I guess you know the recurve, but anyway, the recurve is defined over a field of characteristic 3 by these two equations. Okay, n0 is a power of 3, and n is 3 times n0 squared. Now, can we say something about the full automorphism group in the zero P rank case? The answer is yes, but only in the even characteristic case. What is the reason? Earlier, I recalled the new approach from the book, okay, using deep group theory, starting from the trivial intersection property, okay? 0 P subgroups have trivial intersection if the P rank is 0. Now, groups with this property have been classified for P equal to 2 by Suzuki, Schultz, and Hering. And we don't have the same results for P greater than 2. So that's the reason why this theorem holds only in even characteristic. And let me go through it very quickly. P rank 0, even characteristic, if the automorphism group fixes no point, then either the group is solvable, and if it is solvable, then the Hurwitz bound holds. Actually, a stronger bound than the Hurwitz bound, 72 times G minus 1. If the group is not solvable, of course, it can have many more automorphisms. But when this happens, more precisely, when the group is larger than 24G squared roughly, then the possibilities for the commutator are known, are just a few possibilities, and for each of them, one can compute the genus of the curve. Actually, we can say something also in the odd characteristic case, and this result is already in the book. P rank 0, odd characteristic, the automorphism group fixes no point. If the group is solvable and P squared divides the size of the group, then we have a quadratic bound on it. Okay, second problem, Nakajima external curves. What do I mean by that? Curves attaining this bound here, okay? Bound for the size of a P group in the positive P rank case. So gamma is positive, S is a P group. The precise Nakajima bound is P over P minus 2 times G minus 1. Together with Gabor, we investigated curves attaining the bound or almost attaining the bound. What do I mean precisely? Curves admitting a P group of size between these two values. They are very close, actually, as you see, because both the fractions are close to 1. Okay, what is our result? Under those hypotheses, we show that either the P group actually has size P, the curve is ordinary, and the genus is P minus 1. Or X is actually a Nakajima extremal curve. It is the upper bound is actually attained, and the curve is a ramified Galois extension of a curve of the first type. When it is a Nakajima extremal curve, when the bound is attained, then we prove that the full automorphism group is the semi-direct product of the P group by a subgroup of a diagonal group of order 2P minus 1. Okay, it's possible to say something about the full automorphism group of the curve. Actually, this is just one possibility. The other possibility is more technical and holds only for P equal to 3. Okay, third problem, Nakashima's bound for ordinary curves. Now we are here, ordinary curves, Nakashima bound is not sharp. What can we do about that? Let me begin with examples. Examples of curves with roughly, ordinary curves with roughly G to the 3/2 automorphisms. Okay, recall the bound is quadratic here. Now I will present some examples with as many as roughly G to the 3/2 automorphisms. The first example goes back to Subrau, 1975. He pointed out that this very simple curve here, known also as an Artin-Mumford curve, x to the q minus 1 times y to the q minus 1 equals 1, is an ordinary curve of genus q minus 1 squared, and whose automorphism group has at least 2q squared q minus 1 elements. Actually, equality holds, as it was proved later by Valentini and Madan. In Nakashima's paper, we have another example, this one here. And later, other curves with as many automorphisms as G to the 3/2 were found by Guralnik and Müller, Guralnik and Rosenberg and Ziv. More recently, by Henning, Stichelt, and the curve by Stichelt was thoroughly investigated in a very nice paper by Korczmarek, Montanucci, and Pietro Speziale. Let me stop for a minute the list of examples, because I'd like to recall two very nice results. One by Nazar and Gabor, going back to 2005. They characterized the Subrau curve for Q equal to P as the only curve of genus P minus 1 squared, defined over Fp, which contains a subgroup isomorphic to the elementary abelian group of rank 2 over the prime P times the diagonal group of order 2P minus 1. And later, Montanucci and Zini, in some sense, extended this result. They showed that if the automorphism group of the curve which is assumed to have genus Q minus 1 squared, contains an elementary abelian subgroup of order Q squared, then the curve is some kind of generalized Subrau curve. That is, has equation L1 of x times L2 of y equals 1, where L1 and L2 are linearized polynomials. Now, is it possible to do better than G to the 3/2? Now I'd like to stress an interesting fact. We are looking for an ordinary curve with a large group. So the natural idea, okay, let's start with the ordinary curves with the largest possible P group, because we have seen the importance of P groups in large groups. Well, actually, if you limit yourself to extremal Nakashima curves, that is the curves which have the largest possible P group, then you are stuck, because the bound that we saw before is 2 times P roughly G minus 1. So you can do better than G to the 3/2. So you have to look elsewhere. And actually, the right place to look in is a paper by Dixon going back to 1911. Dixon investigated the ratio of these two determinants. Why? Because these determinants are invariant under the action of the general linear group of dimension 3 over Fq. Q is the power of the characteristic. Actually, this is not just a rational function. This is a polynomial. So a polynomial which is irreducible and defines a curve with this genus, Q to the 5/2, roughly. okay? And since the determinants are GL3Q invariant, then the curve is PGL3Q invariant. Okay, so we have an automorphism group of size roughly Q to the 8. If Q is a prime, then it is possible to show that actually the curve is ordinary. Okay, so if Q is equal to P, we have an ordinary curve with roughly G to the 8 over 5 automorphisms. Okay, so we actually can do better than G to the 3 over 2. This curve was studied by Perivelto back in 2009 and by Korczmarek, Timpanella, and myself later. And in these two papers, a number of nice properties of this Dixon curve are proved. Also properties not related to the automorphism group. I forgot to mention that this construction holds for Q odd. What about Q even? But for Q even, we have this nice example by Z. I guess, to my knowledge, it is not published anywhere. It is just contained in an email by Mike Ziv, but it's a very nice example. Okay, the curve is defined by these two equations. The genus is equal to the P rank, so the curve is ordinary, about Q cubed. And the automorphism group contains a subgroup, or it is equal to a group of size roughly Q to the 5. Okay, so ordinary curve with how many automorphisms? Roughly G to the 5 over 3. So again, more than G to the 3 over 2. Now, what about not finding examples, but improving the Nakajima bound? We have this unpublished result by Guralnik and Ziv. Okay, they claim to have proved that if P is odd, then G to the 8 over 5 is the best bound possible. And for P2, then G to the 5 over 3 is the best bound possible. And if it is the case, then these bounds are sharp up to the constants, because we have the previous example, the Dixon curve for P odd and the Ziv curve for P equal to 2. Anyway, to my knowledge, the best improvement, best published improvement of the Nakajima bound is due to Gumbish, Smith, and Wan back in 2015. And recall that the Nakajima bound is roughly 84 G squared. Here we have a bound about 6 G squared. Okay. Oh, time is running. Time is actually running a lot. Okay. So let me skip some parts. Now I'm going to deal with large groups in the intermediate case. Okay, it's a very difficult problem to find a bound, so we will deal with special curves and special groups. First, solvable groups. Okay, genus at least 2, odd characteristic, intermediate case for the P rank. With Gabor, we show that if the group is solvable, then it can have more than 84 G squared elements. Then we have results for a strange condition, genus even. Okay, this is a very nice phenomenon. I'm afraid I cannot discuss it, but the key remark is this remark here: if the genus is even and the characteristic is greater than 2, then we have this purely group theoretical condition. Any 2 subgroup of the automorphism group has a cyclic subgroup of index 2. And the proof is just an easy exercise. It's a straightforward consequence of the Riemann-Hurwitz formula. Okay, but it has a lot of nice consequences because, again, we can use deep results from group theory. For instance, the classification of 2 groups with a cyclic subgroup of index 2. So when the genus is even, we can say a lot of things. For instance, in the intermediate case for the P rank, we showed in Gabor that if the genus is even, then the size of the automorphism group cannot exceed 900 G squared. And also we can say something else, which I'm going to skip. Now, go back to the ordinary curves. We have special results for the soluble case and the even genus case. This is just a brief summary. Gabor and Maria, 2019, show that if P is odd, the group is solvable, the curve is ordinary, then we have an upper bound of 68 times root of 2g to the 3 over 2. And the nice fact to underline is that this bound is sharp. Okay, and an example is the Stichtenot, the Cauchy-Varosh-Montanucci Speziali curve. Then Pietro and Maria found nice bounds for the G-even case, both in the non-solvable and in the solvable case. Okay, as you can see, very recently, other results have been obtained by different authors. For instance, Gabor and Maria in 2020 dealt with D groups of size and power of a prime D, different from the characteristic. Nurda-Gulambar and Burchin-Gunesh with nilpotent groups. Nazar, together with Pietro, groups of prime order. In all these papers, bounds for the size of the group with these properties are found, and examples of curves attaining the bound are given, if not characterizations. Okay, and we saw Monday afternoon for you, the very nice paper by Pietro about their results with Nazar on groups of prime order. I'm going to skip the details. Okay. Now, only just two cases remaining. Simple groups. Okay, we know the importance of simple groups in the theory of finite groups. With Gabor, we dealt with the simple groups for the genus even case, and of course non-abelian simple groups, and we found only these 5 possibilities. Okay, simple groups, non-abelian simple groups for the G-even case are only this one, and this is a result that I like very much. For each of these cases, we have examples. Finally, groups fixing a point. For a group fixing a point, the best known general bound is due to Singh back in 1974, and is a bound of roughly g cubed, okay, 4g cubed over p. Together with Gabor, we found this this bound here. If the size of a group fixing a point exceeds 30 g minus 1, then we have some constraints of the p rank, surprisingly. The p rank is 0, or the p rank can be written as a formula like that: p to the k minus p to the a minus p to the b plus 1. Now, relying on this result, Stefano Ria and Marco Timpanella proved this very nice theorem. They showed that if you have a group fixing a point with more than 12 times g minus 1 elements, and if for that point the second ramification group is trivial, then the curve is one of these two curves here. Very, very nice result. And one of the curve is ordinary and the other has 0 p rank. Okay, let me check the time. Yeah, I'm almost done. I would like to say something about maximal curves in the context of automorphism groups. Yesterday, we saw the beautiful talk by Said, so I'm not going to tell you what the maximal curves is, because everybody of you already knows. And I guess you know that all curves appearing in a 0 p rank classification are maximal over some finite fields. Okay, let me skip this part. I promised you that we would have encountered the Fricke-McBees curve again. And here is the Fricke-McBees, which was introduced as a Riemann surface back in 1899. But Top and Verskor in 2018 found a Jacobian decomposition for this curve valid over finite fields, valid over characteristic P equal to 1 or minus 1 mod 14. And they show that the Jacobian decomposition is just the 7th power of an elliptic curve. And by the key result by Tate back to 1966, we know that if this elliptic curve is maximal, then the curve is maximal. And actually, it is maximal for an infinite number of characteristics. Okay, the curve is fp squared maximal for p 71, 251, and so on. For p equals 71, the curve is not Galois covered by the Hermitian curve. And this is a result obtained by Fernando together with Bartoli and Maria, published this year, and was obtained where in the last visit of Fernando to Perugia. It is related to this problem. Yesterday, Said recalled that a conjecture by Fernando is that all plane maximal curves are covered by the Hermitian curve. And we also have a similar problem. Okay, we know that there are infinite families of curves that are not covered by the Hermitian curve, but we don't have fp squared maximal curves not covered by the Hermitian curve. We don't have them yet, so we don't know if they exist, but sporadic examples exist. Okay, my last slide. In the same paper, Fernando, together with Daniele and Maria, they proved that for a maximal curve, if the Hurwitz bound fails, then the curve must be a quotient of the Hermitian curve for fields of order a square over prime. Okay, so another, I mean, let's say if there is a curve not covered by the Hermitian curve over fp squared, then it cannot have too many automorphisms. Okay, if the number of automorphisms exceeds the Hurwitz bound, then it is a quotient of the Hermitian curve. Okay, this is a result that I like very much, and it is also bound, sharply bound, because the Friedmann curve is a maximal curve attaining the Hurwitz bound, which is not a Galois cover of the Hermitian curve. Okay, last year, during the Mass following the passing of Fernando, the Mass was broadcasted in Facebook, and in the chat I saw a sentence in Portuguese, "Obrigado por mundo." Please forgive my Portuguese. And that's what Fernando actually was, a gift to the world. Thank you for your attention.